Our last section today is going to discuss how to work an equilibrium problem if we have a very large equilibrium constant. All the problems that we've been working so far have had very, very small equilibrium constants. Some of our solubility equilibria have been 10 to the minus 10th or 12th or even 33rd. A lot of our Kas are at least 10 to the minus something. But what happens if we have a big equilibrium constant? And I'm going to say, if it's large, we're going to say it's greater than 100. I mean, so far we haven't had anything bigger than, I think he used 4. I think I worked one yesterday where, it was maybe 50. But if it's bigger than that, we're going to have issues making some of the assumptions that we've been making. We have, for most of our problems, we have been assuming that K is going to be small. We can drop some of the minus X's and plus X's, we can drop them out because the changes are so slight. But when K is large, that's not going to be the case. First of all, what does it mean if K is large? Well, if an equilibrium constant is large, that means that the reaction goes almost all the way to completion. Okay, because if you remember, equilibrium constants are the concentrations of your products over the concentrations of your reactants. So if that K is big, that means that your concentrations of your products are very, very large also. And so that means I'm not going to have very many reactants left. And so if I start a problem that has reactants with it that I've been given, I can't assume that X is small because it's going to almost go all the way to completion. So I have a sample problem here that I'm going to work for you. Because we skipped the section on successive approximations, some of the example problems that he worked aren't going to fit our purposes very well. So that's why I've got a different one to work here. So let's look at this problem. Calculate the equilibrium concentrations if a 5-liter container initially contains 15.9 grams of hydrogen and 294 grams of iodine. You can see that my equilibrium constant is 710, so it certainly classifies as a large equilibrium constant. You're going to have some equilibrium constants that are up 10 to the 4th, even 10 to the 5th. This one is certainly large enough to qualify for this particular kind of problem, though. And then you'll see the equation. Now, I don't want you to get confused because, yes, I did use this same equation yesterday. But yesterday I told you that the temperature was like 448 or something. And now my temperature is much lower. And you'll see that my equilibrium constant is much higher because we've always talked about before how equilibrium constants depend on the temperature at which the reaction is taking place. So don't let this, don't think I'm just like making things up because the temperature was different. So that makes the equilibrium constant change as well. All right. Well, for starters, if we're going to work any kind of equilibrium problem, we have to know concentration, and what I've been given is grams. So that's the first thing that I've got to do here is figure out what my concentrations of these guys are going to be. So for my hydrogen, I have 15.9 grams of hydrogen, and in 1 mole of hydrogen, there are 2.02 grams. And so that is going to give me 7.87 moles, okay? Now, I have 7.87 moles, but it is in a 5-liter container, so if I divide that out, that is going to give me 1.57 molar hydrogen. All right, let's look at the iodine now. For the iodine, I had 294 grams of iodine, and in 1 mole, there are 253.8 grams. And so when you crunch those numbers through, you end up with 1.16 moles. And so then to calculate concentration, you're going to take 1.16 moles divided by 5 liters. And that's going to give me a concentration of 0.232 molar iodine. Okay. Now, because this is going to take up so much space, I'm just going to take these concentrations and I'm going to copy them over up here so that I have them. 1.5 molar H2 and 0.232 molar I2. And we'll erase this so that we've got some more space. Okay. Another trick that I'm going to show you here that I can employ is that because I divided both of these by the same volume, I can actually use this in my equation because I have the same ratios that I did before. So initially here, my hydrogen is 1.57 and my iodine is 0.232, and this is nothing because I don't have any. Now, this is what I was trying to explain earlier, and that's that because I have a large K, when I get done, almost everything is going to be over on the product side, and this is not, I'm not going to have hardly anything left on this side over here. Then if I would go to subtract X here and subtract X here and add X over here, or actually it would be 2X on this side, this is not a small change. And especially since I'm going to have a squared in my equilibrium expression, I could end up with all kinds of nastiness in trying to do that algebra. And I would have something that I would, likely have a difficult time working. So when you have a large equilibrium constant, we apply a little trick, and that's this. First of all, I am going to pretend that I'm going to go take this reaction all the way to completion, because in reality, it is going to go almost all the way to completion. So if I go almost all the way to completion, my limiting reactant is the iodine. So there's not going to be any of this left. And that means that I'm going to have 2 times 0.232 on this side. Now, why 2? Because for every 1 mole of this, I make 2 moles of this. Okay, again, one of those places where you have to watch your coefficients. So I'm going to have 2 times this. This, I'm going to have 1.57 minus 0.232, which is going to give me 1.34. So that's going to be at completion. But because it is equilibrium, part of it is going to reestablish equilibrium. It's going to kind of bounce backwards a little bit, but most of it's over here on this side. So at equilibrium, this is going to be 0.464. I went ahead and multiplied that out, minus 2x, because I got a 2 in front of that. Okay, this is going to be x, and this is going to be 1.34 plus x. Okay? All right, so that's what I'm going to have. Now I can set up my equilibrium expression. So my equilibrium expression is going to be concentration of HI squared over concentration of hydrogen times concentration of iodine. Okay? So my equilibrium expression, 7.1 times 10 to the second. HI is 0.464 minus 2x quantity squared over 1.34 plus x times x. Again, nasty, nasty, nasty looking, but I'm going to assume x is small. And because I've already said this is going to go to completion and just going to bounce back a little bit, it should be small. So I'm going to assume x is small and go ahead and not worry about these small changes. So I'm going to ignore this piece. I'm going to ignore this piece. And then I don't have anything that's nearly as bad to work. So when you crunch through all that algebra, you end up with an x of 2.27 times 10 to the minus 4th. And certainly a number like this is not going to affect these guys here, so my assumption is valid. Okay, now I have to actually find equilibrium concentrations, and so if this is x, that means my I2 is the same as X, so the concentration of I2 is 2.27 times 10 to the minus fourth. The concentration of H2 is 1.34 plus X, but again, it didn't affect it. It's so little, it doesn't make a difference. So this is 1.34, and then for my HI, it's going to be 0.464 minus 2 times X. Again, this is too small to make a difference, so this is 0.464. Okay? And all of those would be molarity. Okay? So, when you have a large K, you can't work the problem with what you're initially given. If they tell you to start with the reactants, you can't work it with what you're initially given, because that is going to go almost all the way to completion. So the trick that you employ is you pretend it goes to completion and say what that looks like, and then let that equation bounce back and reestablish equilibrium, because then X is small and you can ignore these and make your math actually doable. Okay, so that will be the last section that we cover for this module.